Good morning, good afternoon, good evening from wherever you are. My name is Jake Shermeyer. I'm a research scientist with CosmiQ Works, and joining me today to present this as well is
Hogan. I'm a data scientist with CosmiQ Works.
Today we're going to be talking about SpaceNet and specifically the SpaceNet 6 challenge. We'll be discussing generally what SpaceNet is if you're not familiar with SpaceNet. We're going to talk about the challenge structure. We're going to go over what the data set is, and also we're going to be talking about our algorithmic baseline that we built for this challenge. So if you're not familiar with what SpaceNet is, SpaceNet is a non-profit LLC managed by CosmiQ Works. It's dedicated to accelerating open source artificial intelligence applied research for geospatial applications, specifically geared towards foundational mapping. Our present partners are Cosmic Maxar, AWS, Intel AI, Capella Space, Topcoder, IEEE GRSS, the National Geospatial Intelligence Agency, and Planet Labs is our newest partner for 2020 and 2021. SpaceNet is really about 4 specific pillars. We curate high quality labeled data sets. In this case, it's all satellite or aerial imagery. Thus far, we have 11 cities in the full data set, over 900,000 building footprint labels, and 20,000 kilometers of road labels. And this encompasses over 26,000 square kilometers of satellite imagery. And I should mention that all of this data is open source. It's made available through the AWS Open Data Program. So you can go and download this data today, and we'll share a little bit about how you can do that near the end of this presentation. Thus far, we've had 5 challenges hosted on Topcoder and have awarded $250,000 in total prizes. Today, we'll be discussing the 6th challenge, which actually just concluded on Topcoder. We're entering into the final scoring stage here. And we've had over 1,300 submissions worldwide. That number has actually more than doubled since SpaceNet 6. So that's making real progress. The challenges really attract some of the highest quality participants and some of the best data scientists in the world who actually compete in these challenges. So we've seen real success with this format. Beyond the challenges, we also open source several algorithms. So the main outputs from these challenges are algorithms that these data scientists create. 13 of which we have open source are geared towards building detection, and another 10 are focused on road detection and routing. Finally, our 4th pillar is evaluation. So this is really how to best benchmark performance for multiple tasks, whether you're interested in the best way to extract building footprints, how do you evaluate such things, or road network extraction. We also have metrics that we've built geared towards that. Finally, we also have a very active blog that features detailed analysis on a lot of the challenges as well as the data sets that you can read, and we'll share the links for that down the road here in the slides. So our open data sets, the SpaceNet data sets, really we focus on 4 more pillars here. So we're really focused on quality. Most of all, we want to ensure that the label quality is really the best and the highest that we can get. Goes through several quality control rounds. We have structured taxonomies that we create prior to creating these labels. And they're rigorously reviewed and tested by us before we actually release them. The availability of open data is also critical. And licensing, more particularly, is really something that's often overlooked, but is absolutely essential for broad market adoption. So we open source everything under a Creative Commons Attribution Share Alike 4.0. This means not just academic researchers, but also corporate entities can download and use our data, which we're super excited about to make it available to everyone that you can build both research and products on top of the SpaceNet data sets. Thirdly, accessibility. The open data set must remain open after our specific events, so in this case, our challenges, and that it must be easily accessible in the cloud. And this is why we host it through the AWS Open Data Program. There is no requester pays. So basically the data set is freely available. You can download terabytes of data for free to your hard drives today at no cost to you. All you have to do is open up an AWS account to do this. And we have guides as to how to do that if you're not familiar with this. Our final piece here is interoperability. Specifically, this is going to be cloud optimized geotiffs. So creating our data and making the data be able to be displayed in a cloud optimized format, so you can load it in a web browser, basically share it, build web-based mapping applications. That's a crucial piece. The spatial temporal asset catalog is another one, so standardized metadata, so people actually know what the data is, what's contained in it. And again, this just increases interoperability and transferability to new places and new people. And finally, the last two pieces here I touched on a little bit already, was the standardized labeling taxonomy. So really ensuring that things are standardized in a consistent format, and more specifically having clear evaluation metrics. So your IOU thresholds are apples metrics, some of the more technical things that we've worked to build and curate. So I'll turn it over to Daniel to walk you through our cities and some of the other pieces of the SpaceNet offerings.
Over the course of the 6 SpaceNet challenges, a variety of data has been open sourced, and that includes 11 different cities from 5 continents and showing a great range of geographic diversity. For each of these cities, we've open sourced high-resolution electro-optical data. In the case of the Atlanta, USA dataset, the data also includes views from many different off-nadir viewing angles, all taken within a few minutes of each other. And in the case of the Rotterdam dataset, we have our first multimodal dataset, including not just high-resolution electro-optical data, but also high-resolution synthetic aperture radar data. We take these large 16-bit geotiffs and tile them down to smaller sizes for competitions for ease of use, typically 200 meters on a side. The imagery, however, is only half the story. The other half is high-quality labels. And for many of the cities, specifically 8, we have building footprint labels available, which together total 900,000 buildings. For 9 of the cities, we have road network labels available, which altogether comprise 20,000 kilometers of roads. Next slide, please. Central to how we approach SpaceNet is the systematic way in which these challenges are designed. So each challenge is more ambitious than the ones that came before it. But at the same time, each challenge refers back to the ones that came before it, so that the lessons learned can be drawn forward to help solve new problems. The first SpaceNet challenge, which began in late 2016, asked challenge participants to find building footprints in overhead electro-optical imagery of Rio de Janeiro. The second SpaceNet challenge had the same task, but brought geographic diversity into the mix, with 4 different cities from 4 different continents. SpaceNet 3 looked at extracting a completely different kind of information from the imagery. Instead of buildings, looking for the network of roads. And in the course of doing so, SpaceNet 3 introduced a new algorithm for evaluating the performance of road network extraction, which has proven to be quite useful. SpaceNet 4 returned to the issue of building footprints, but brought it into a more real-world situation where imagery isn't always from exactly overhead. It is often from a very off-nadir viewing angle, which makes for a more challenging problem. Addressing that was the focus of SpaceNet 4. And SpaceNet 5 revisited road network extraction, but brought it into a more realistic, real-world scenario by asking challenge participants to not only extract the road network, but also extract reasonable travel speeds on each segment of road, which is the missing link needed to estimate the actual optimal travel routes and travel times and other kinds of real-world things that one would want to know about a road network. And finally, SpaceNet 6, which is now coming to its conclusion, brought multimodal data to SpaceNet with a unique data set of electro-optical imagery combined with synthetic aperture radar. Next slide, please. Over the years, interest in the SpaceNet data releases has only grown. In that time, there have been 530 million hits to the public data repositories, resulting in 678 terabytes of total downloads. We've open sourced 23 algorithms, the best of the best, out of 3,089 challenge submissions over the course of the six SpaceNet challenges. During this time, we've seen requests for data downloads coming from 82 different countries. Next slide, please. So that's SpaceNet in general. For a look at SpaceNet 6 specifically, I'll turn it back over to Jake.
All right, thanks, Daniel. I'm going to be talking a little bit more here about the challenge structure. So our challenge here is a multi-sensor all-weather mapping one. And why do we call it multi-sensor all-weather mapping? Really, that goes to the SAR, or Synthetic Aperture Radar component of the data set. If you're not familiar with SAR can actually penetrate clouds. It can work in all illumination settings, so both day and night. And the reason for this is it's just an active sensor. So it's actually shooting a beam at the ground, which is then reflected off the surface, and it comes back to the sensor. And SAR data really has been underexploited and underexplored, particularly in the computer vision world or the AI research setting. And the reason for this is just a lack of open data that's available. So that was our primary motivation for creating this data set. The data set is centered over Rotterdam, the Netherlands, which is the largest port in Europe. It's over 120 square kilometers of data we've captured. We have near simultaneous collects of both SAR data as well as electro-optical data. So if you're not familiar with EO, that's just kind of how our eyes see and a little bit beyond into further wavelengths. And what I mean by near simultaneous is it's within a few days of each other. We're not talking within minutes. But rather days, which is totally okay for an application like building footprint mapping. Our labels in this sense, what we're interested in mapping is going to be 48,000 building footprints. So we're going to, our competitors, our participants were asked to build AI algorithms that could automatically extract building footprint labels using mostly SAR data, but with the choice to augment with EO as well. And I'll talk a little bit more about that. So our two primary challenge goals, we really wanted to baseline the performance of AI algorithms to detect buildings in SAR imagery. So as I said, not a lot of SAR data out there. We're not really sure how well these will do in this case. And the second goal was to test if EO data can be used to augment or improve SAR imagery in any way. And I'll talk about how we structured the competition to really incentivize that. So this is the SpaceNet 6 timeline. So we released the data in early February 10th. So as I said, you can download that today via AWS. The challenge started on March 16th. We released an algorithmic baseline, so basically starter code that Daniel created to help our participants get started and spun up on this challenging problem. From there, the challenge ran the whole way until May 1st, and right now it is the end of May, and we are finalizing our scores, getting the final leaderboard set, and then we will be awarding prizes and announcing our winners on June 4th. The Total prize structure here is we had $50,000 in cash prizes, so 20,000 went to first place with 2,500 going down to fifth. We also give out $15,000 in AWS GPU compute credits for participants. So if they meet a certain benchmark, we then award a $500 credit for them to spin up their models and do some training that way. Our challenge ultimately will conclude on June 14th at CVPR EarthVision, which is a workshop associated with the Computer Vision Pattern Recognition Conference. And this is one of the leading AI computer vision conferences in the world. So we're really excited to be included here. We will be sharing some of the results of the challenge and just talking more about the data set, and also having some of our winning participants share kind of what worked for them and what was novel about their solutions. We also have a paper about the data set. So if you want to go deep, you can read quite a bit about the SpaceNet 6 data set through the EarthVision proceedings. And then just to talk about the data set overview. So more specifically, what is in this data set and why is it structured in such a way, and why should you care, basically. The SAR data here is provided from Capella Space. So Capella is one of our newest SpaceNet partners. They're a startup. They will be launching their first sensor very soon into orbit. But this is actually a test collection from Capella. So they've mounted one of their sensors, a very similar sensor at least, to what they'll be launching to space, and then wanted to test the capabilities of that sensor but before you actually get it into space. So this comes from an aerial collect. So an airplane is actually flying these image strips, and the collection dates span a small portion of August here. So August 4th, 23rd, and 24th of 2019. 204 image strips in total. And if you check out the graphic on your right here, which has been spinning through, the background of this graphic is our electro-optical data from the WorldView 2 satellite from Maxar. The SAR data comes from this Capella aerial collect, and these are these individual image strips that are being collected. So this is just kind of one pass of the aerial flight, and these are the literal flight lines as they happen, sped up quite a bit, obviously. But this is, I believe, from the August 4th collection. So the details of this data set, it's quad polarized. So for your SAR fanatics out there, that means we have all four polarizations. So that's the maximum you can have. Basically, this is how the wave is distributed from the sensor and returns, how it's spun and polarized. The spatial resolution here, the raw sense is 0.25 meters. We distribute the data at 0.5 meter after some pre-processing. The alternator look angle in this sense is 55 to 57 degrees, which is pretty standard of SAR collects. So if you're curious about how we build this data set a little bit more, some of the pre-processing that we do to really get it into a challenge-ready format here, we work with the SLC data. We align and co-register all four of the polarizations, and then do some fine code registration, really to ensure that things are closely georeferenced to the Earth as well as they can be, and that all four polarizations align as they're supposed to. We calculate the amplitude of the SAR data and then square it to get intensity. And then we perform a multi-looking algorithm, which is basically a noise reduction step with an average convolution in a 2x2 kernel. From there, we convert the polarization intensity to decibels. So this is just a unit conversion. And then we georegister and ortho-rectify and save the quad polarizations into a 4-channel image at 0.5 meter resolution. And the image on the right here, we have, so you can see some of the SAR data. So this is a mosaic of some of the image strips, and you can see it's really beautiful data. The building footprints here are outlined in red. So a lot of different activity here in Rotterdam beyond the building footprints. You can see the oil tanks, some ships. Interesting thing about SAR imagery is how taller objects will bounce back and appear closer to the sensor. So you can see some of that happening on the right side of the image with that boat. The top of the masts actually start to lean back towards where the sensor is, appearing that they're actually closer to the sensor, which is an interesting phenomenon of SAR data. So the second piece of our data set here is the electro-optical imagery. Our collection date here is from August 31st. So again, this is about a week after the last image was collected of SAR. We've got Worldview 2 imagery in this case, which is pre-processed in our standard format that we've done for all of our past challenges. So this is atmospheric correction, to surface reflectance units, then orthorectification. So again, we're making sure that the terrain is accounted for when we're doing all of our georeferencing here. We've got 4 channels of imagery in this case, so red, green, blue, and near infrared. Again, this is half meter, so it's the same resolution as our SAR data. The base resolution of this before pan sharpening is 2 meter data. We also distribute that, and our off nadir looking here is 18.44 degrees. And then just to talk about our annotations, we worked with the 3D bag data set from August of 2019 also. So this data set is actually curated by the Netherlands Cadastre. So this is their land registry and mapping agency. It spans the entirety of the Netherlands in this case. And this data set, actually, the 3D component of the 3D bag data set comes from a LiDAR collection. So each building actually has height estimates as well. So we didn't ask competitors to actually use this height data or try to predict the height of buildings, but that's something that you certainly could do, and that's something we're going to investigate in some of our post-challenge analysis here. Ultimately, we come down to 48,000 buildings included in the final data set. We do throw out areas that don't have enough labels, which happens very occasionally. And we do also dissolve some building footprints together. So in some senses, a lot of these buildings here might have row houses here. So they might, individual addresses are actually represented in the raw data set. We end up merging those together to make sure that individual buildings stay together in this case, as it's just simply too challenging to map individual addresses from space at this point. Finally, we really do a lot more pre-processing really to get this into a challenge-friendly format. So we have basically EO and SAR pairs for each location, and we tile the data to 450 meters squared or 900 pixels on a side. A lot of current AI algorithms need data that is tiled into smaller formats. You can't just feed in really super expansive satellite images into these algorithms and expect them to work. It's really geared towards smaller images, so that's why we do this. So in a sense, we first tile the SAR data, and then we tile the EO data to match the extent of the SAR tile. And from there, we then, the EO and building footprints are also mapped to the extent of the SAR images. You notice these images are a bit rectangular here. And the reason for that is it's clipped off on the side, as sometimes the image strip just isn't exactly square. So we want to make sure we account for that. We then split the training data into 3 sets. So we have a training set, a testing set, and a scoring data set. So the training data set we distribute to all of the to everyone, and that has both the all of the SAR, all of the EO data, as well as building footprints. Then we have a testing and scoring data set. We distribute the testing data set, and in this case, the testing data set actually only contains just the SAR data, no labels. And then we set up a leaderboard through our challenge site, which is Topcoder. Participants will submit, will have the imagery, run their models in the imagery, and then submit proposal outputs to this leaderboard. And the leaderboard will then tell them whether the proposal is good or bad in a numeric format. And then finally, the algorithms will be scored once more on a final held back scoring data set. that they haven't seen before. And the reason we do this is to ensure that algorithms really can generalize well to new areas. Another little niche fact here about this data set is that the training data set contains both SAR and EO. However, the testing and scoring sets contain only SAR data. And the reason we did this is we really want to see how well algorithms can do just scoring on SAR data alone. However, we also want to test if having EO data and maybe doing some sort of pre-processing steps to transform your SAR data to look more like EO data, to perhaps pre-train your models on the EO data first before switching to SAR, to do some colorization, other interesting techniques. We wanted to test it if that would really add any value. And then, in a real use case scenario, while you might have historical collections of EO and SAR in some locations, but when you actually go into the field and you're doing your work, you might only have SAR data. So can you use that historical EO data in the sense to pre-process and improve that SAR collect in some way? And that's why we structured in this case, and we were hopeful that participants might be able to figure out a way to best use this EO data. So for section 4, I'll turn this back over to Daniel. He built our algorithmic baseline, and he will walk you through what that means and what that entailed.
At the beginning of each SpaceNet challenge, we release an algorithmic baseline. Next slide, please. The algorithmic baseline is a complete solution to the challenge problem. And the idea is to provide a starting point, either in terms of code or just ideas that challenge participants may elect to use as they begin to go off and develop their own solutions. So this slide shows some images of the baseline at work. The first two images are example optical and SAR imagery, as would both be available during training, as Jake noted. Then during testing, only the SAR is available. So the third image you see here shows the baseline algorithm's best attempt at extracting building footprints from just the SAR imagery. And comparing that to the ground truth building footprints in the fourth image, you can see that there's an overall correspondence, but also room for improvement. So one of the things that makes the baseline for SpaceNet 6 unique is that this is the first time our baseline is built off of Solaris, which is an open source Python library for geospatial deep learning that was recently introduced by CosmiQ Works. And Solaris provides tools for the entire geospatial deep learning pipeline, which typically begins with tiling out large imagery files, taking vector labels and turning them into raster masks corresponding to those tiles, and then training a deep learning model and using it for inference. The inference output in the form of pixel masks can then be converted into vector labels, which can then be evaluated using various standardized performance metrics. So all of these steps are made much easier than would otherwise be the case using the tools within Solaris, and all of them have been used in the baseline. While we're on the topic of Solaris, part of what makes it so valuable is that it can be used to compare different models and other differences of approach. So for example, if you have two researchers both developing solutions or potential solutions to a geospatial problem, they might have different Python environments, different Python versions, different GDAL versions, different deep learning formats or frameworks or hardware types, and it makes an apples to apples comparison very difficult. But with Solaris, there's a uniform environment in which it's very easy to slot in and out different deep learning architectures, even comparing TensorFlow models to PyTorch models, and other kinds of changes, all specified in a simple configuration file which allows for faster prototyping and research and development of effective models to solve one's geospatial deep learning problem. Next slide, please. So that's Solaris, and what we built with it is the baseline algorithm. The baseline here has at its heart a deep neural network, which has a UNet architecture with a VGG11 encoder. The first half of this network combines information on progressively larger geographic scales to get a big picture understanding of what's going on. The second half of the model takes that information and propagates it back down to smaller scales, ultimately producing for each pixel a prediction of whether or not it is part of a building. And then from those pixel maps, vector outlines can be produced. Now, this is a standard technique in computer vision, but to work with SAR data, we had to take some of the unique features of SAR into account. One of those things is the geometric effects that make the directionality from which the imagery was taken important. Jake mentioned, for example, the layover distortion in the case of the ship's masts, which you see here in the image for buildings next to the side edge of the water. And so we took directionality into account. Another thing is we wanted to take advantage of the information in the optical data. And we did that with a transfer learning approach, where the model was trained first on the optical data to learn the basics of extracting building footprints from overhead imagery. And then it was retrained on the SAR data to specialize in working with the kind of data where we wanted it to perform the best. To evaluate model performance, we use what we call the SpaceNet metric, which is an evaluation metric that has very elegant simplicity to it. The way it works is for every predicted building footprint, you define it as correct if it has an intersection over union with a ground truth building footprint of at least 1/2. And then you compute the F1 score for correct building footprints. The reason why this is a good metric to use is that it penalizes the right sorts of things. If the algorithm misses a building entirely, that's penalized pretty heavily. But if an algorithm just gets the exact location of the walls a little bit wrong, that's penalized lightly, if at all. And so the metric corresponds with our common sense conception of what it means to perform well on a task like this. So the baseline algorithm's performance by this metric is 21, which is a number that doesn't mean anything in isolation, but to put it into some context, if we forego the transfer learning, then the score drops to only 14, indicating that there was value in that step. And it slides actually a little bit more if we ignore the directionality, which can be important for SAR. So there are many other ways that models like this could be improved. The most direct one is to play around with different model architectures and different hyperparameters, trying to optimize performance. One could go at it from a domain adaptation angle, trying to convert a SAR problem into something more like an optical problem. And one could also look into the literature of SAR analysis algorithms extending back decades. So there are many ways to approach this problem. Looking at what challenge participants have done is the next step. Next slide, please. And for that, I will hand it over to Jake.
Thank you, Daniel. So looking at our public leaderboard, this is where we sit as of May 1st. As I said, our winners will be announced on June 4th. So currently right now what we're doing is we're retraining a subset of these top algorithms. And then from there, we will derive our final scoring on that final held back test set. So these scores will change a little bit. There will likely be some movement in who moves up and who moves down. These are right now where we're at. So you can see the baseline at the very bottom there. It's now currently in 53rd place after starting out as the top solution. And this isn't a bad thing. This is a good thing. We put the baseline out to see, as a entry level, first crack at this problem. And you can see that people have really improved on that baseline since then, more than doubling it. Most of the top 10 have doubled that score, which is really encouraging, showing a lot of progress, and it really shows the value of this challenge setting and crowdsourcing what's happening in this domain. So look out for the full winners announcement on June 4th. And if you would like to reach and dive deep into some of the other things we have a ton of material out there. I am Jake Shermeyer. I'm the challenge manager. Daniel Hogan was the second speaker. He was the baseline lead. We also have several other contacts in other organizations. Ryan Lewis is our general manager of SpaceNet, and Jason Brown was the Capella Space lead and the SAR providing company for this challenge. So just to look at and check out some of these other information channels, if you're interested in seeing or working with Solaris, that's right now on the CosmiQ repo, so github.com/cosmic. The SpaceNet repo is also there, and that's where we have all of those winning algorithms. So if you're interested in building footprints or road network extraction, or really any other geospatial problem, these could be great starting places for you to look at some of the best techniques right now, state of the art for extracting building footprints, or really any other mapping feature. You could extend these to other problems. If you want to learn more about SpaceNet, some of the historical challenges we've run, or download our data set, you can go to spacenet.ai or check out the SpaceNet data on the Open Data program. We have an active blog, CosmiQ Works, the downlink. So we talk about SpaceNet frequently there, as well as some other geospatially relevant topics and research that we've done over the years. We also have a podcast, so if you enjoy hearing Daniel and myself speak, then you can certainly check us out on Apple Podcasts, Google Play, Spotify, Stitcher, and SoundCloud. The title of the podcast is Training_Data. Don't miss that underscore. And we're also on Twitter, so if you want to twit some tweets at us, we're at SpaceNet _AI, CosmiQ Works, Maxar, Intel AI, or AWS Cloud. Yeah, and that's our presentation for the day. We thank you for your attention, and thanks for viewing.